I'm not Alexei. I am Simon Talaba. I will give you a spin-off of some of the topics that Alexei talked about. And in particular, in the next 3 lectures, I want to discuss a phenomenon which is what we may call a cherry pie of turbulence among physicists. And this phenomenon is the phenomenon of intermittency. So of course, this buzzword will need to be defined. And in today's lecture, I want to define this word and in particular talk about what turbulence look like, or what fully developed turbulence look like. And so this lecture today will be, I will call it statistical patterns. Statistical patterns of turbulence. And so I will start from the starting point of this lecture is again the Navier-Stokes equations that we talked about in the previous course. But this time I will put an initial ingredient which is a forcing, the force on the right-hand side. And of course, this has to be supplemented with the incompressibility condition. And here we can, at least for the sake of the discussion, take x in R3, for instance. And the picture that we had, or that we have at this very moment, was the following picture. So I will take the picture that Alexei drew yesterday. We had the Navier-Stokes equation for which this is time, for where basically there is actually at least a belief that solution exists globally in time. And then there is the Euler, obtained by putting essentially mu equals 0. And we discussed, Alexei discussed that, okay, Euler, there's probably a problem up until some certain time. And that basically this is the matter of blow-up, short-time existence. So of course, what we want to do is to let nu goes to 0 in this picture. And after this possible blow-up time, we know that there is a problem. Okay? So here, up until some finite time, we'll say, okay, there is this will be a discussion for future work. And today, what I will discuss in this diagram is what happens on the right-hand side of this diagram. So from here to here, which in a sense corresponds to the limit when you let t go to infinity. T going to infinity. And so this problem is a problem that actually has been investigated a lot, not so much by mathematicians, but by physicists and doing either experiments or numerical simulations. And the question that we may ask is, okay, in this limit here, when you let t goes to infinity, what do we see? What do we see? So typically, if we think about an experiment, a common way of investigating the properties of those equations with apparatus is to use a wind tunnel. So you have some flow that goes in this direction, agreed, and then poof, you make a probe sufficiently far away from this entry, and you measure signals. Here you measure. And typically, what you see is something random. So this is so can we switch? So typically, if the viscosity here is small enough, or equivalently if the Reynolds is high enough, what we see is that you take you measure, for example, the velocity as a function of time. You see something which is incredibly random. But at the same time, if you change the Reynolds number, this is an experiment which achieves a Reynolds number of the order of 10 to the 6th. And the two pictures show what's happening on this probe, but at two different times. And the observation is the following. So whatever the initial time you take t0, here time to 0 prime, well, the kind of signal that you see look the same, roughly. It's random. There's a signal apparently random. But on the other hand, there is no way to distinguish one signal from the other. So in this sense, it looks also very much reproducible in a statistical sense that we will define later. Statistically reproducible. And so such a state, which so in the sense that it does not depend on time, possibly does not so much depend on Reynolds, does not depend on the experiment. So such a signal that is statistically invariant with respect to time, the community calls a statistically steady state. Statistically steady state. Of course, so this is an experiment. So the question would be, okay, how does this result connect to the Navier-Stokes? It's not so clear. Well, in the recent years, there has been a lot of numerical simulation of the DNA of the Navier-Stokes as well, where in a sense you impose a random forcing and you integrate the Navier-Stokes for a very long time. And this is essentially what you see. So that's this is what you see. So this is a brute force investigation of this equation at with a finite value of nu. On the left panel, what is plotted is the magnitude of one of the components of the velocity. And on the right panel, it's a cut along the line which is shown with dots. And in a sense, the remarks that we can do are exactly the same. It is apparently random. And it does not seem to depend upon the time. And so the question is, okay, if we take for granted that this signal is what it is, then we have to describe it with a language of stochastic processes. Description required in terms of stochastic processes. Okay. Now, what is perhaps, of course, so we have this, so if we come back to this picture, so here it seems pretty clear from numeric that we need to have probabilistic description. Okay, so of course the question that we may ask is, okay, how come this is probabilistic when we started with something which may be, okay, which a priori, if this is the equation that we consider, it is apparently deterministic. Well, as you may guess, probably there is lots of things going on here. This is outside the scope of those three lectures. But basically, the idea is that here, in order to justify the fact that we are going to use some probabilistic description of turbulence, we can think about different causes. So first, we can think that instead of looking at those equations with a deterministic force, we can assume that force is random, or sufficiently random. We can also imagine that initial condition of this equation, initial conditions are sufficiently random. And so this the connection to a deterministic framework is essentially left for future discussion. Left for the future. Okay. So now we are in a position to state what we want to do and to state some working hypothesis that we are going to work with in order to formulate the problem of describing this kind of turbulent measure in a suitable sense here, in a certain limit when nu goes to 0. And the working hypothesis that we are going to do are the following. So working hypothesis. The first hypothesis that we are going to do to make is that for all nu, positive, there exists a physically relevant steady state, a physically relevant measure. I'm going to define it in more details later, but we can write in this way. Nu, which is accessible either through time averaging, in the sense that for any observable phi, which may depend upon the velocity field at that solves the Navier-Stokes equation. This is the limit. This is can be computed as the long time limit of the time average. Phi of u of s. Yes. So this is what we call an ergodic hypothesis. We are going to discuss it later. And of course, it can also be accessed through ensemble averaging. And the second hypothesis that we are going to ask is if there is a certain limit for this guy. And so one way to formulate the problem is the following. If we control the forcing, so that essentially such that the energy input Fu nu average over this statistically stationary measure is prescribed. For all nu and independent of nu. Independent of nu. What becomes of this measure? What becomes of nu is to say, is there a way we can describe the limit when nu goes to 0 of the average with respect to nu of any observable? And this object here is what we would like to call the turbulent measure. The quantities if they exist are what we would like to refer to as the turbulent measure. So basically, the steps are the following. We take nu finite, we let time go to 0, we obtain something steady, we compute averages, and then we go this way. Of course, we don't know whether those averages can be reproduced by Euler, but this is a subject for other discussion. So now that this series of observations have been done, observations and working hypothesis. So it's clear that I will want to take you in I want to use in the next couple of lectures the language of stochastic processes and random variables. So for the sake of completeness, I will just here do a very crash course on the vocabulary of random variable and stochastic processes. Survey of probability theory. So that we can adopt short. So it will be clearly only very partial. If interested by, to have more serious references, one can take a look at the, can take a look, for instance, at Paviotis. Which one? This one? Blue is good? So, priorities, there are good lecture notes by events as well. Lecture notes on probability. Probability. For example. Okay. So the vocabulary. So of course, since, there will be a lot of definitions. The first definition is a probability space. So we assume that we are working with an underlying probability space, which will be a triplet of quantities. So this is a space of realization. Realizations, an ensemble of measurable events, and a probability measure. Probability measure. And so typically, property of F is that it has to be stable by complementary complement and countable unions. The property of P, so that's a sigma algebra. Typically, NP is a probability space which has the property that, of course, it takes elements of the measure, it takes events and has usual properties. So that the probability of disjoint ensemble is P of AI. Sorry. Plus P of AJ. Okay. So that's the probability space. Now, in order to prove this probability space, usually we need a random variable. So random variable is essentially a function which goes from the space of realization, typically toward a set. So if this set is real, we are going to talk about continuous random variable. If it's discrete, let's go n, z, it will be discrete. And essentially what we require is that this X defines a law of probability, which is a natural measure induced by the probability on this space, which we write mu of X of a certain event I, which belongs to the measurable events of S, typically intervals if R is real, which will be the probability of the inverse. And this we write as well P of X in Y. Okay. So there is also, so in a special case when if so in a special case when S is real, so we can define probability density function. So density function. Typically, if S is, for example, real, so in the case of continuous random variable, we will typically define f of x, which will be the law of the event up to x. It's the probability that x is greater than x. And this is called cumulative density function. And well, if f can be derived, then usually we will work with the derivative of f. So p of x equals d of x dx is the probability density function. PDF. Now with those elements we can compute averages. So if x is a random variable, say continuous, then the average we will write x is the integral of x of omega p of d omega. And this can be computed also with the density function, which will be simply x of p of x, x for x in R. And naturally, those are definitions that they update to higher dimension. So if this is x, and so we can also, so this is the average, so the mean. So more generally, for a functional, for any functional phi of x, this is the integral of p of x Tx. And an example which is useful is take phi equal the exponential of Tx, and this will give you the characteristic function which is a function which depends on the free parameter t. It's simply the average of EITX under the law mu. Okay. Example, of course, this will be useful. We can take a Gaussian random variable. In which case, P of x will be something that will have a Gaussian shape, which will be parameterized by two parameters, the variance and the average. In that case, we have x equal mu x square minus x square equals sigma 2. And the characteristic function is minus T2 over 2 sigma square EITU. Check. And so this quantity, I mentioned it, I didn't write it, this is the variance. Okay. So we have the random variables. So now we can, so this is the first break that we need. The second break that we need is the notion of stochastic process. Stochastic processes. Definition. And a stochastic process is simply a parameterized collection of random variables. Raised collection of random variables. So if so this is the index set, and again if t is n or z, then we say that x of t, x is a discrete stochastic process. And if t is real, then x is continuous. Okay. So there is nothing incredible here. The useful quantity, though, that we we want to work on is basically is to be able to define some probability distribution for those stochastic processes. And in particular, if we have in mind that so typically when we work with continuous stochastic process, so typically this kind of guy that we see here, then we need to be able to talk about the probability distribution of those objects. And a convenient way to do it is to define the finite dimensional distributions. Distribution. This is FDD. So we're talking about, we have X, which is a real stochastic process, and the finite dimensional distribution is simply the collection of all laws mu of k, or T1, Tk, mu k of x of T1 is in certain interval, x of Tk is a certain interval. Is equal to probability that all of the indices are in this interval. If we want to mu k of A1 T1 AK Tk for k in n and T1 Tk in R. Okay. So basically, we have a continuous. We have what it simply means is that if we have a continuous. If we have a continuous random variable, like a velocity field, what we are going to do is simply probe it on how many, the number of points that we want. We can take infinitely many as long as it is countable, and the set of all the joint distribution of the multi-valued random variable defined by those set of points will define the finite dimensional distribution. And actually, there is of course, the question that we may ask is, okay, if we know those finite dimensional distribution, does this prescribe the stochastic process? Okay, so in general, this is not true, but this is true if the underlying stochastic process is continuous. Observation. If xt is continuous, almost surely, then the FDD fully determine xt. And this is, I think, see again the reference. Capabilities, chapter 1. This is chapter 1. Okay. And now that we have that, we can define a very important concept, which is the equivalency law between two statistical processes. So, equivalency law. So if you have two processes, x and y, then we say that x and y are statistically equivalent, like this, or are equivalent in law, if the FDD of x equal FDD of y. So if all the so of course if x and y are not continuous, okay, you may have two processes which are equivalent in law, but those properties can be very different in terms, in particular, on the regularity of the sample path. But if they are continuous, this condition fully prescribes the stochastic process. So this is an important topic. Do I want to tell you something else? Yes. So this equivalency law, and so we are just going to define some processes that will be useful for the future. So one class of process which is important are Gaussian processes. So, okay, first definition, a multivariate Gaussian. So, c'est a random variable. X1. Xn is so multivariate Gaussian. If and only f, there is it has a certain density probability, which is right. If f of x1, xn equal 1 over 2 pi n cn, and exponential of minus 1/2 of x minus mu transpose c minus 1 x minus mu, where c is a matrix with dimension n times n, is a positive matrix. And mu or n is a vector. Okay, so that with this definition, we have the average of x is mu, and the correlation between xi minus mu I, xj minus mu j is Cij. Okay. And so examples include important ones. So examples of Gaussian processes. So we have Brownian motion or inner process. This is a Gaussian process such that C of T and S is so the minimum on T and S, and mu of T for 0. Okay. And the second example is the Ornstein-Uhlenbeck process. Uhlenbeck process. Which is again a process which we can think that lives in take values in R, and which has a correlation function, so which has which is centered. It has 0 mean, and it has correlation xt xs, which is the exponential of minus alpha t minus s. And with that, we are going to make a small break and come back in 10 minutes. Break. Okay, so let's resume our business. So we have been talking about Gaussian processes, and now it's time to just mention another very important class of stochastic processes, and those processes are the stationary processes. So definition first. So xt, we always think, well, okay, we always take processes which are continuous and say without loss of generality that lives in R. And so we say that so x is strictly stationary when essentially the process which is obtained by time shifting for all s, the process x of t plus s obtained for t than 0, so we are just shifting this guy by s, is equivalent in law to the original process. Okay. Well, the equivalence in law is well understood in terms of the finite dimensional distribution. And so in particular, for a strictly stationary process, x of t1 plus tau has the same law as x of t1. Okay. So this means that for all tau. So this means, this means in particular, so this has also the same law as x of 0. Okay? This implies that the average is constant in time. Is constant in time. U of t is nothing but x of t, and this is nothing but the average of x of 0. Okay. And the second implication is that if we look at 2-point statistics, x of t1 and x of t1 plus tau has the same law that x of 0, x of tau. Okay, so this in particular implies that the correlation of the process x of t plus tau x of t, which a priori should be a function of t and tau, is in fact, I'm shifting by t, is in fact a function of only the difference in time. Okay. And so usually this motivates So usually this kind of condition is very strong because it involves comparing the finite dimensional distribution of two processes for up to an uncountable set of points. But actually, so that's why it's a strong version of stationarity. And when we look at a signal like that, it's absolutely not clear that this guy is strongly stationary. But what we can check is that those two conditions may be valid, and this motivates a weaker version of stationarity. Weak stationarity. It's xt is weakly or second order stationary when essentially there is a function c from R to R such that the correlation t plus tau minus mu is c of tau, and of course you need to have a function, and you need to have a constant mu, the average to that x of t equal mu. This is just a weak version of stationarity. And what can we say from that? Actually, it will be enough to prove some ergodic properties. And just so exercise, clearly, if we are weakly stationary, we are weakly stationary, but the converse is not true. So weak stationarity does not imply strong stationarity. Okay. So so the good thing is for a signal which is weakly stationary, we can define, depending on the properties of the correlation, we can define some interesting properties, and in particular the correlation time. So if interestingly C is in L1, if the integral between 0 and infinite of C is finite, we define the correlation time as tau C, which is the integral between 0 and infinity of C ds divided by C of 0. Exercise. Show that for the Orstein-Uhlenbeck process. With u equals 0 and c of tau, which is the exponential. The correlation time is 1 over alpha, for example. So this we have. So this is just an interesting quantity to compute. And basically, the idea is that if the correlation time, or equivalently this C is in L1 is finite, then stationary processes have nice ergodic properties. And so typically, just an example of an ergodic theorem. This is just an example. There are stronger versions that exist. So we take a process which is weakly stationary, such that so we call okay, x of t equal mu, and the correlation function is c of t is L1. Then we are guaranteed that the integral over time of x of s ds minus the average is going to converge in an L2 sense to 0. So in particular, okay, so this tells us that essentially, of course, this applies to a prescribed stochastic process. If we want to compute functional of this process, we need to verify that the correlation time of the composed stochastic process is finite. But if it is the case, then essentially computing time averages allows us to recover the properties of the underlying measure. So this is true for t goes to infinity. And for a proof, just again refer to those notes. The proof is direct, actually. Just employ to expand the square. And just as a remark, so in summary, essentially, roughly said, so if the core is finite, then time average equal ensemble average. By this theorem. And of course, here we have chosen to, because it was suggestive. So if you are thinking about mathematics, this guy is mute, so it represents anything. But we can think about this variable either as a variable with respect to a time variable or a space variable. Okay? So in particular, if So T is represents a space variable. So basically, we have something like XR for R greater than 0. Okay. Then the correlation time will be a correlation length. Then correlation time becomes a correlation length. Correlation length. And in that case, an orthogonal average can be replaced by a space average. In that case, space average equal time average. Okay. So this is a very okay. So this is there is nothing to say, but actually, if you actually, it has some impact when one wants to analyze a signal, because well, for historical reason and for essentially a problem of money. When investigating turbulent data using experiments, one usually has an easy access to time averages. One puts a probe somewhere and measures the signal, and then we average in time. And poof, we hope to get something which represents an underlying measure. But with DNS, with direct numerical simulation, which are very costly, it's very hard to integrate for a very long time in time. But rather, we can have a very detailed description of the field in space. Actually, so this picture that we can show again, I kind of lied to you at some point. But so when you see it moving, here, so the fact that it moves through as a function of the parameter is the altitude. So it's a 3D. So it's a 3D direct numerical simulation, and we are just scanning the cube at different levels, at different altitude. So what you see here actually is not a reflection of the time stationarity, but of the space stationarity. In other words, this is what we call a space homogeneity. And this remark actually will be useful for now, as we are going to discuss the so-called HIT, the homogeneous isotropic turbulence, under the framework of a certain number of hypotheses. Statistics of homogeneous isotropic turbulence. So of course, the question is the one that was formulated at the beginning of the course, so this lecture. So what are statistics of such an object? In the limit nu goes to 0. So here, if we look at the data here, for the result from the numerics, the point of contact with the Navier-Stokes equation is there because we have integrated them. But the question is, how do we connect the properties to any properties of the Navier-Stokes equations? Can we do it? And if yes, what are reasonable assumptions to implement and to require for the stationary measure? So this is perhaps one of the main breakthrough of the 20th century in terms of for turbulence, and a framework was proposed by essentially Kolmogorov in 1941, and the connection between the measure and the Navier-Stokes equation will have to do with symmetries. So I will present this, and so this is inspired very much, adapted from fresh legacy, in chapter 5. So, hypothesis. Kolmogorov, 41, hypothesis. It says the following say. In the limit of nu goes to 0, provided that we are controlling we are controlling the energy injection rate, all the symmetries of the Navier-Stokes equation broken by the presence of forcing and dissipation are restored statistically at small scales. At small scales. Okay, that's the first hypothesis. So this is the first hypothesis. So here we are talking about essentially the symmetries that were discussed in course number 1, I think. So symmetries which, so if we think about continuous one, thinking about rotation, time, space, translation, and scaling. So the second assumption is a statement about what is what the scaling symmetry becomes. So the scaling symmetry is prescribed by a single exponent h. Okay, and the third, which is not formulated this way in Frisch, but which in essence is this one, it's h equal 1/3. 3 hypotheses. Okay. So let us try to remember what it means and what it implies for the statistics of the steady state. So, typically, so what does it mean? Translation. Translation means that, okay, we take, for instance, the easiest one, time. So this prescribes that under the U of xt, which is considered a stochastic process in x and t. So x in r cube t. Okay, so this is equal in law to u of x t plus tau for all tau. Okay, so space is u of x plus r0 and the time is equal, equivalence is equal in law to the statistics of u x t. So u x t, let's put it this way. Equals r0 t in law. Then we have rotation. Means that u of x t is also the same as what you would get by rotating both the x coordinate and just rotating u at the same time. O u of x t, sorry, for O in SO3 of R, orthogonal matrix, and scaling symmetry. It means that u of x t is equal in law to lambda h u of x over lambda t over lambda 1 minus h. Yes? So this is basically the first hypothesis. And the second hypothesis, yes?
Why would the anticipation break the starting symmetries?
Okay. I don't know if you remember, but so typically when we are talking about so the time and space symmetry, rotation, I think, we don't care about. So if we apply them to the Navier-Stokes, it's okay. We can have dissipation. But if we apply scaling symmetry, then you have to rescale nu at the same time. So yeah, you just do the math, and you have to rescale it by essentially a time times a velocity square. And so basically, this is an example of a broken symmetry due to the presence of forcing dissipation. And of course, if you have some forcing, then the symmetries that you impose may be also broken by the presence of forcing, depending on its features. It depends. So this is. Yes, and of course you may also argue that rotation is usually broken in DNS because you are working with a periodic box. So boundary conditions are such that in fact you don't have rotation at large scale. The statistics are not rotationally invariant. But if you go for scale which are small enough, again we are going to describe that, maybe they will be restored. So H equal 1 third here. So it's maybe it's interesting to. So this is a statement about the finite dimensional distribution, as we've defined previously, and so it's interesting to take a look at what those series of equality imply for simple statistics. And so we are going to take simple statistics like 1-point statistics and 2-point statistics in order to see whether those assumptions are reasonable or whether they are totally wrong. So let me see. Yeah. 1-point statistics. So under the hypothesis 1, 2, 3, essentially one can find that each component of the velocity field is universal and independent of both space and time. What does it mean? It means the following. So if you take UI, whatever you want, which is at a prescribed point in space and in time, then this guy is equivalent in law to UI of x0, 0 by time homogeneity. Stationarity. This is the same equivalent in law to UI of 0, 0 by space homogeneity. And then we can rotate it, okay? And then this is law to u x, for instance, of 0, 0 by rotation, isotropy. This rotation. And that's it. So it's univocally prescribed. And in particular, observe 1-point statistics satisfy scale invariance. Trivially, because you can rescale this guy by anything, which is 0 by 0, and it's okay. So is this true? Let's check it. Okay. So this is an example of. So in this example, you can check, for example, whether. So this is whether, for instance, the 1-point statistics of ux obtained by space averaging the signal is the same as the space average of ui, for example, which are, if those hypotheses are reasonable, it should be true. And so let's observe it. The PDF. Or this one. So on the left, on the left you have the PDF of ux on the right, you have the PDF, the density probability function of Uy. The data is shown in pink. It's normalized by the variance. Okay, so that Ux is centered and as a variance which is unity. And basically, we can see that both PDF looks very much identical and are basically described by a Gaussian function. So this seems pretty much okay. Actually, one can check that in wind tunnels that we discussed previously, we observe exactly the same thing. So for example, in those experiments, which well, this time we are sampling the time. Okay, so 1-point statistics in time. If we make averages, so this is averages with where what is different between the two is what is different between the two signals. Basically, the initial time at which you're sampling the data. You have the same amount of data but shifted in time. What you see is that the PDF that you observe for this one-point statistic is the same, more or less. It seems very robust. So in that sense, okay, time-space rotation, at least for the one-point statistics, it seems to be pretty reasonable. Okay. So the question now is, okay, what does those equality in law become, for example, for two-point statistics? Is it still true? And so this we are going to see, and we are first going to see what this implies. Two-point statistics. So this should relate to the statistics of, say, U of x1, t0, U I, uj of L0 plus, say, R t0. Okay. And so we will, a quantity which is traditional to investigate in turbulence is rather than to work with the joint test statistics, we would have two variables. We are going to make one out of two. So we are going to define a quantity, which is also a cherry pie of turbulent data analysts, which are the so-called increments. And what we define is delta V of x separated by a vector L will be simply the difference of velocity between 2 points at the same time. So this is x here, x plus L here, and then you have V of x plus L t. Here you have V of x t. And the increments is just measuring the difference between those two quantities. And so it's customary to introduce, so this is a two-point quantity, but it's also it's already a complicated quantity because it's a vectorial quantity. So we are going to simplify things again, and we are defining the longitudinal increments. which will be, which we will write delta V with a parallel here, which will simply be the difference x plus L t minus V of xt projected on the direction of the separation. Okay. Unit vector in the direction of the separation. Okay, and so this is a quantity which, okay, again depends on x and L. Okay, and similarly, we can define also transverse increments, which will be, we can write delta V perp x L, which will be nothing but this guy here, delta V of x L projected along a vector which is perpendicular to the separation. Okay, so classical. So why we do that is basically because those quantities are scalar quantities. Scalar quantities. Easier to manipulate, easier to measure. Simply that. Okay, and so the statement, okay. And so in order to probe the statistics of those guys, we are going to introduce some quantities that are suitably averaged, and those quantities are the so-called structure functions. Structure function. So we define SP of, say, parallel. We are going to take parallel, right, which is equal to delta V parallel of x L t average with respect to the unit measure and taken to the power p. Simply that. And of course, we can introduce the transverse structure function, which is delta V parallel P average. Okay? So then, we can make a statement about the behavior of the structure function, which will be very much akin to the statement that was erased here. Properties. Under the hypothesis, again, 1, 2, 3. 1, 2, 3 of the Kolmogorov framework. SP parallel, SP perpendicular are functions of L only, where L is the scalar distance Okay. And so to see this, let's just look at the statistics of, say, delta V parallel. Delta V parallel of X, L, T. Okay. So this is so this is this quantity. So this is the projection of the full velocity at X, L, T by definition. And so this is equivalent, the same statistics as L scalar V of 0, L, 0 by, so this is homogeneity plus stationarity. No. So homogeneity plus stationarity. And then one can do, and one can apply the rotational symmetry to this guy. Okay, and so delta V parallel of X, L, T should be equivalent in law to, so if we rotate both L and V on the same side, it should be the same law as delta V X of 0 in the, say, X direction. 0. So that SP equals delta V parallel P equal SP of L. Okay. Which this is a function of L only. Function of L only. Okay, and now we can try to see what scaling variance produce. Okay. So scaling. And the scaling, the statistical scale invariance imposes. So SP of L, it's delta V X of 0, L of X, no, sorry. This means that this guy here, delta V X of 0, L of X, 0, should be the same statistics. So I divide this by L as L over lambda, EX 0, 0 delta Vx. This I multiply by lambda H. Okay. Now if I take lambda equal L, I get lambda, I obtain L to the power H of delta Vx of 0 Ex 0. Okay? So this means, this implies in particular that SP of L is LH, so L to the power H times P times SP of 1. Okay? And so let us define the so-called ZAPs, which are scaling, some scaling, which will reflect what's happening here. So the logarithm of L of SP of L. So L goes to 0. So that S of P of L equal L to the power zeta P, sorry, SP of 1. Oh, sorry. Then the statistical scale invariance. This is SSE. Imposes that psi P equal PH equal P over 3 by the third hypothesis. Okay. So we have a way to probe scale invariance. And so in particular, if we feel a bit insecure by the fact that we have put this H out of the blue here, we can try to formulate scale invariance in a way where H is not going to play any role. Okay? And so a convenient way to test scale invariance will be to take a look at the ratio between transfer function. Okay? A convenient way to probe statistical invariance, consider ratio such as SP over SQ to the power P over Q. So this should be behave as L to the power psi P minus P over Q psi Q as a function of L. And so if should be constant, especially if psi P equal PH. In particular, P equal 4, Q equal 2 defines the flatness of the signal, flatness F equal S4 over S2, 2, sorry. And this should scale as L to the power psi 4 minus 2 psi 2. 0 if SS is valid. Okay, so let's see. And let's try to measure the flatness in an experiment. So this is taken from the data have been gathered by Laurent Chevillard in his habilitation thesis, and essentially those this plot represents the flatness of turbulent signal, so the ratio, exactly this quantity, as a function of L. So on the right side, here, those are the large scales, and on the left side, those are basically the small scales on which we would expect chromograph hypothesis to apply. And what we see is that regardless of the experiment and of the Reynolds number here, which is involved, the data collapse, and they show that this quantity here is not zero. It's not zero, and it's rather something which is very close to 0.1. Observation. Psi 4 minus top psi 2 approximately equal to minus 0.1. Clearly. In numerics, we can do the same thing. In numerics, so this is not the flatness. So this is, for reason, this is a different normalization where we plot, we take p equals 3 and q equals 3 over p. So scale invariance should materialize essentially in those ratios being flat as a function of the scale. And what we see is that they are anything but parallel. Okay. So if we plot as a function of the order the zeta p as a function of p, this is what we see. So the red line is the pure similarity prescribed by a chromograph, p over 3, and the points are what we measure. And you see, in particular, flatness. You can see it's a bit different here. And if we were to measure, well, the question is, maybe it's close to minus 0.1. Okay. But to investigate this in more details, I will left it for discussion tomorrow. Yes. And well, we will see basically. So tomorrow we will see whether this kind of data is compatible with this observation, and then we will try to see how to model such behavior, and what does it mean in terms of the structure of the velocity field. That's it for today.